Section A is probably the most challenging part of it. So let's have a look. It's to do with the temperature of a beaker or a body. And this is the time at 0, 1, 2, 3, 4, 5, 6. So these different times, it has these different temperatures. The first thing you have to do is you have to estimate the temperature loss. And effectively, the way you do this is by having a look at this statement. So at 1 minute, we're going to estimate the temperature loss is going to be the difference between the numbers either side of 1. So find this difference, and then what we're going to do is we're going to divide by 2, because there's 2 jumps between 0 and 2. And you're going to repeat that process for the rest of this table. Now, the second row of the table is a little bit more complex or a little bit easier depending on what you think about it. And it says the difference between the temperature and the surroundings. So the surroundings is 20 degrees. So what you need to do for this row of the table is have a look at the difference between 2 numbers. One of the numbers is going to be 20 degrees, and then the other number is going to be the temperature in the room at that particular time. So at 1 minute, it's going to be 93.8. So you're going to have to find the difference between 93.8 and 20. Last but not least, you are going to collect this data and you're going to go onto Desmos. On Desmos, what we're going to do is we're going to plot a graph. The way we're going to plot a graph is by inserting a table and putting these values in. Once you've done that, you're going to write y equals mx plus c. And it's going to look like this. Now, you can move these sliders about and you're going to see if this straight line matches with this table of values. Because in this particular investigation, we're looking for a heat flux constant, that means there's going to be a constant relationship between the two of them. So as one increases, the other one's going to also exactly increase. And what I mean by that is, let's see if we take a sample table where we've got a range of x values, and let's say our range of y values are going to be as follows. You can see here there's an exact pattern. And if we actually move this m here to 10, or let's move it to 5, let's see if this is working. And we're going to zoom in a little bit. Now, you can see there's an issue with this because our straight line doesn't match up with these green dots. So let's change C to 0. Now, this is what we're looking for. So at the end of the section A, you're going to look for something that has a straight line relationship, number 1. And number 2, the way you explain it is every jump we go up in 1 in the x-axis. This particular example is going to jump up 5 in the y-axis. So that will jump up 1, so it goes from 0 to 1 for the x, and the y would go from 0 to 5. And then this one we're going to jump up 1 in the x-axis, 1 to 2, and then 5 in the y-axis, 5 to 10. So our heat flux constant in this instance is going to be 5. This will be different for your investigation, and the reason why is the gradient is exactly 5. Now, the heat flux constant wouldn't be 5 if you put it at 10, because you can't get from one variable to the other exactly by multiplying by 5. That wouldn't work. But what's really special when you have a y-intercept of 0 is that you can predict anything in the graph. So let's say we went to when x is 20. Now, because when x is 20, and because we've got a relationship here where the straight line goes through the 0, 0 coordinate, there's an exact ratio between these two numbers. Any graph which goes through 0, we will have this relationship that to get from the x to the y variable, we just times by a multiplicative factor, and it's always the same regardless of where you are on the graph. So you can see here to get from 40 to 200, we multiply by 5, and this is because it has a gradient of 5. Now, I'd like to carry on and talking about the rest of this with you. Now we are going to study a exponential graph. So the easiest way to do this is to type in exponential graph into Desmos, and once we bring that up, we are going to get the following. We'll get an exponential function, and we get to play around with these different coordinates here. Now, if you have a look at the investigation, it says A, B, E, K, and X. So let's change the letters a little bit to match up with this. That's the first thing you need to do. And then we're going to move these sliders to match our actual graph that we've added in before. This is really quite an easy part of the investigation, and then it says 30 degrees and 40 degrees. So what you need to do for this part is decide whether the temperature is on the X or the Y, find where it says 30 or 40, go to the graph and just read off the X value, or if you were reading from the X axis where 30 is, you go to where 30 is, you go up to the graph and you read off what the Y value is. Now, last but not least, I'd like to briefly talk about this. It says the heat flux constant is the same for this section, despite the temperature on the outside changing to 3. So the easiest way you would do this section of the investigation is by copying this particular table and pasting it at the bottom. And what we're going to do is we're assuming that to get from one variable to the next, there's going to be a multiplicative factor that you've already discovered. So you're going to be able to work out, for example, what this row of the table would be, and then using what the multiplicative factor is, work out what this row of the table is. I'm not going to give you too much hints for C because it's quite straightforward when you know that factor.